Hi everyone, this, I'm Kram Kim, a program manager at the KGTSEC, the KIAT-Georgia Tech Semiconductor Electronics Center at Georgia Tech. Uh, in this session, we brought Dr. David Citrin, a professor in School of Electrical and Computer Engineering at Georgia Tech, and we're gonna hear about his research themes regarding on the terahertz non-destructive evaluation for microelectronics packaging and beyond. Let me briefly talk about his biography. Dr. Citrin is a professor. His research centers on terahertz technology, nanotechnology, and advanced imaging for non-destructive evaluation of materials. He has received the Presidential Early Career Award for Scientists and Engineers and the Frederick Bessel Award from the Alexander von Humboldt Foundations. Let's welcome Dr. Citrin.
Hey, thank you very much for the introduction. Very pleased to have the opportunity to tell you a bit about our work related to microelectronics packaging. All right, I'd like to divide my presentation into three parts. Uh, the idea of terahertz techniques are probably not familiar to everybody, so my introduction will take some time. So I want to discuss why terahertz spectroscopy and terahertz time-of-flight tomography are potentially interesting for microelectronics packaging. And then I'll move on to some examples. I'm actually going to start with some introductory examples that are not directly related to microelectronics packaging, but I think they're quite clear. And also, they might give you some ideas related to packaging, and I would be happy to hear from you about it. And then I'll proceed to discuss some of our work on packaging, after which I'll conclude. So to begin, let me talk a bit about terahertz generally. So the terahertz band of the electromagnetic spectrum lies at longer wavelengths than the infrared and at shorter wavelengths than the microwave. So we're talking about wavelengths if we go from right to left. So if we start at the microwaves, starting at about 3 millimeters down to 3 microns. So by convention, people talk about the terahertz band as being frequencies from about 100 gigahertz to 10 terahertz. Other names for the terahertz band, roughly speaking, are submillimeter waves and the far infrared. So it's a part of the spectrum where there's been little technological work until really the middle of the 1980s. And interest in terahertz exploded with the development of ultra-fast optical techniques. So why are terahertz interesting? Well, apart from being a different part of the spectrum that can contain interesting information, for imaging, shorter wavelength means higher resolution if we compare things to microwaves. But from the point of view of non-destructive evaluation, as we will see, terahertz radiation penetrates many electrical insulators that might be opaque to visible and infrared light. So we might be able to solve some problems that are very difficult to approach using optical techniques. It's also a non-ionizing radiation, so there are no known health risks involved in terahertz. So unlike X-rays, X-rays can present hazards to human operators. Another competing technique for many applications is ultrasound, but some of the materials we're most interested in are actually quite lossy to ultrasound, to acoustic signals at very high frequencies that we would need for high resolution. So terahertz, in some cases, is really the only option we have to try to look inside materials and components, whether we are interested in finding defects in manufacturing or to be looking for failure in service. So, some of the topics we work in, so roughly speaking, under the heading of non-destructive evaluation, NDE, material characterization, quality control. We work a little bit in pharmaceuticals, not much, some in biomedical applications. We work on art and archaeology. And of course, as we'll see, we work on advanced packaging. Now, terahertz, whether you've heard of it or not, is not that commonly used, but it is used in industry more and more. So at the bottom of the page are some examples where it is actually used in production or in in-service inspection. So how does it work? So how do we generate terahertz electromagnetic signals? And there are a number of different ways to do it, but we in particular are interested in generating very short pulses of terahertz radiation. So on the right is a terahertz pulse. It's roughly a single electromagnetic cycle. Now, the way it's done in the system we use, and in many cases, is based upon a photoconductive switch. So a photoconductive switch is a piece of intrinsic semiconductor with metal electrodes deposited upon it. There is a voltage applied between the electrodes. So ordinarily, the gap between the electrodes is an insulator. However, if an optical beam or pulse is incident upon the semiconductor and the photon frequency or energy is above the band gap, it generates electron hole pairs. So when this, let's say, short sub-100 femtosecond optical pulse strikes the photoconductive switch, it generates carriers, and there's a current transient. And that current transient generates the electromagnetic pulse, the terahertz pulse that we see on the right. Now, to do this in practice requires not only the generation of the terahertz pulse, but also the detection. So for instance, here we have that ultra-fast laser that generates the pulse. And the output of that laser is split into two optical paths. One optical path is going to be used to generate the pulse. So here is the, the terahertz emitter. But the other optical path is going to be used for detection. So this is the receiver. So first of all, we generate an optical pulse that is converted into a terahertz pulse, shown here, that impinges upon some sample. So here's a simple case. It's a coating, such as paint, on a metal substrate. So when that pulse hits that coating, we're going to get a reflection from the air coating interface, and then also a reflection from the coating metal interface below. So the reflected signal is going to have two pulses separated in time, determined by the thickness of that coating. So we can measure the amplitude and phase of this reflected signal by adjusting the time delay of the detection beam path and varying it. So in fact, by doing this experiment many times, millions of times, let's say, we can map out the reflected transient, its amplitude and phase in time, and then by analyzing that transient that we measure, we can, for example, in this case, determine the coating thickness on that metal substrate. And maybe if there's a defect between the coating and the metal, some inhomogeneity, we would see that as a different sort of signal in the region of the defect. So this is done in a typical system. It's done at about 100 megahertz repetition rate. We use a commercial system. These systems cost about $200,000 with all the useful options. But as we'll see, prices are coming down fast. There are much less expensive systems these days, more in the $50,000 range. So the black trace here is a typical terahertz signal, roughly a single electromagnetic cycle, about 3 or 4 picoseconds long. And all the signal that follows is the ringing resonances in atmospheric water vapor. And the inset here shows the power spectrum. So we have signal from, about 50 or 60 gigahertz up to about 3 terahertz, and then this is just noise. But here in this power spectrum, we see features associated with atmospheric water vapor absorption. Now, we can get rid of that in two ways. We can remove the water vapor by flowing dry nitrogen over our sample during the experiment. Or since this is reproducible, we can get rid of it due to denoising, signal processing tricks. So we're measuring the amplitude and the phase of the electric field in time. We can work in transmission or reflection. We can do imaging or spectroscopy. Just for the rest of the talk, a point measurement on a sample is called an A-scan. If we raster scan in 2 dimensions and render the data that way, that's called a C-scan. If we render the data for a given cross-section, and we'll see examples, that's called a B-scan. Now, anybody can make these measurements. So where we put most of our work in is the analysis of the data. So the analysis and post-processing of the signals. So as we'll see, that process is called deconvolution. And the deconvolution then reveals the structure associated with the signal we measure. This is the signal produced by the apparatus, but likewise, we can measure the signal after interacting with the sample. So there are 2 main types of experiments we do, and we'll see examples. So we do spectroscopy. So because we have a broad bandwidth in our pulse, we can gather the spectroscopic data over that bandwidth all at the same time. We also do 3-dimensional imaging, and we'll see how that works next. It's called time-of-flight tomography. So spectroscopy is most easily done in transmission through the sample, while time-of-flight tomography is most easily done in reflection. Now, there's one other relevant experiment I want to mention, which we do not do. We don't have the equipment. It's called electro-optical terahertz pulse reflectometry. So this technique is used, you can mount a packaged bunch of chips, and you can basically test the chips as well as bonds by sending a signal through this special probe, high-frequency probe station into the assembly, and then basically looking for anomalous reflected signals. So you can find a short circuit or an open circuit. Usually the way this is implemented is just to find an anomalous signal, then you know your structure is bad and you can throw it away. This actually doesn't really use the bandwidth at very high frequencies, more of the lower frequency range of the output that we saw before. But this sort of equipment is used in industry, in testing of assemblies of various sorts. So I want to go back to what we do, and the key experiment we're going to see is called time-of-flight tomography. And the idea is similar to work that's done in geology for many decades. So here is a source of low-frequency pulsed acoustic radiation. It's sent into the ground. It's detected by these phase-sensitive, these lock geophones. And then by taking that data, one can reconstruct the rock strata underneath the ground. We do this essentially electromagnetically. We send in a terahertz pulse. So here is a cross-sectional rendering or a B-scan of a glass fiber reinforced polymer. So this is a set of thin layers of polymer that also incorporate woven glass fiber fabric. So what we see is we send in a terahertz pulse from below, and what we're looking at is the reflected terahertz signal as a function of position across this cross-section. So we can see the various layers in the structure, and here we see both in the transverse direction and depth, we see a delamination. So this is an area we work in quite a bit in composites, looking for defects in composites that have occurred either in manufacturing or due to impact. So again, this is just a clear example. We're going to go eventually to examples from advanced packaging. Now, just to point out how this works, so we send in a signal like this, we get a reflected signal. So for example, here's that example we saw before, a painted coating on, say, metal. We get these different reflections, we call them echoes. And the time delay between the various echoes tells us how thick that coating is. We have to know the refractive index of that layer or have a good idea, but we can then map out, if we do this experiment across the sample, we can get a mapping of the thickness of that layer. Okay, this factor of 2 is because to do this requires a round trip of the signal through the layer. Almost never do we have to worry about multiple reflections, though it's included here because, well, in some cases, they're evident in our experiments. Now, the key problem is what happens when the layers are thin. When the layers are thin, the different echoes overlap in time, and it looks just like one echo. So one is not able to extract the thickness of the layer in that case when the echoes overlap, so we need to work much harder. And that's where signal processing and now machine learning comes in. So this is where we spend most of our time. So usually the experiments themselves, getting the data is not that hard. It's the analysis where most of the work lies. And the problem can be viewed as a linear time invariant system. So we know the pulse we send in, we measure it. We know the signal we get out, we measure it. But the question is, how do we figure out what the impulse response is? Because that tells us about the sample. So the problem here is one of deconvolution. So deconvolution is an inverse problem. It can be a very hard problem because the easiest way to do this, one would hope, is to Fourier transform, use the convolution theorem, and recover the transfer function. But because of noise and other issues, that usually doesn't work. So we usually actually use time domain techniques. So here's the same example we saw before. Here's the impulse response from that sort of sample. So it's a set of very short reflected impulses if we had a very short impulse to send into the sample. So really, that's the problem we have to solve. And again, solving this using the convolution theorem really doesn't work, or rarely works. Okay, so let me give some examples and start with some examples that are not from packaging. And our first example is just an illustration. What can we do with this in terms of layered structures? So for example, what if we have a metal, and again, this is not packaging, and a multi-layer paint coating? The idea is to measure all the layer thicknesses in one experiment. How is this actually done in industry? The way this is done is the first layer is put down, then an eddy current measurement is made. Then the next layer is put down, then another eddy current measurement is made, and then the next layer is put down, followed by another eddy current measurement. Now, this is very time-consuming and laborious. It also does not reflect production, where this multi-layer coating might be put down before the previous layer is totally dry. Okay, so the laboratory measurement using an eddy current measurement is not even that realistic. So we can actually do this with a single measurement. So again, these blue curves are actually the experimental signals, but the red curves are after signal processing, obtaining the different reflections that are then used to determine the layer thicknesses. So I don't want to spend a lot of time here, but in fact, it works down to on the order of 10 microns for these materials. Okay, here's another example that's fairly illustrative of what we do. This is to measure what's called secondary mill scale on hot rolled steel strip. And basically the idea is hot rolled steel strip. You start with a red hot steel ingot. It is rolled down to a thin strip, which is then coiled. So this is the kind of steel you see on railway cars, on the backs of trucks. Now, when this steel comes out of the rolling mill, it has a gray coating called mill scale. So it's an oxide coating, which is actually useful because it prevents destructive corrosion from forming rust. So mill scale is formed from lustite, magnetite, and hematite. Rust is mostly magnetite, but fortunately in mill scale, lustite is the majority phase. And it's an insulator, so terahertz can see through it. So we're working with ArcelorMittal to measure mill scale on production steel samples. So here's an example where these are measurements made down this dashed red line on this sample. And here you can see after some processing, we have two reflections. One is from the air mill scale interface, one is from the mill scale steel interface, and then we can extract the thickness of the mill scale. Okay, so we are scheduled to test this out on a production line for ArcelorMittal. So it's a, real world technique that we hope will work in production. Lastly, before we move to packaging, we can do some other interesting things. For instance, detect injection weld joints in plastics or thermosets. And the reason this is interesting is because when plastic is injected into the mold and the different flows meet, where the flows meet is the weld joint. And sometimes it's very difficult visually to detect the weld joint. And that's usually the point, 8 point, or a region where the structure fails mechanically. So it turns out that at the weld joint, the different flows meet, and we can have some as frozen in anisotropy of the polymer. And that frozen anisotropy can be used to detect some terahertz birefringence, and therefore we can determine the location of that weld joint. So this is an example where we really can't see the weld joint visibly. There's no kind of valley, nothing we can see easily visibly, but we can see it with terahertz. So this uses the polarization of the terahertz beam. Okay, so now I want to move to semiconductor packaging. And I'm going to start actually with an example that's a little more general than packaging, but it does have implications, as we'll see a bit later. I want to use terahertz spectroscopy simply to evaluate the refractive index and the losses of materials that might be used for packaging for 5G or 6G applications at 100 or hundreds of gigahertz, or maybe one day at a terahertz. So this is work that was done with the Georgia Tech 3D Packaging Research Center. And let's start with some ENA1 glass, and then we'll also look at some plastics, some polymers. So I want to focus really on, well, here in the time domain, we see typical terahertz signals. Remember, for spectroscopy, it's easier to work in transmission. So we can measure the electric field that propagates through the sample. We can analyze this data to extract either the complex dielectric function or whatever we want, the refractive index, the absorption coefficient, the loss tangent. Now, these oscillations are Fabry-Perot oscillations that we can correct for actually physically. So in these plots, they're there, but we know how to correct for that. Here is the refractive index. So here is ENA1 glass. So we get a good measurement out to about 2.7 terahertz. Out here, we reach the noise floor. So this is not useful information. Here's the absorption coefficient. Again, we're going to hit the noise floor out here. Notice the rapidly rising losses. So this is something that is not fully appreciated by many people, that many materials become very lossy at hundreds of gigahertz and at terahertz frequencies, materials that people call low loss for millimeter wave applications. So here's those growing losses. This is actually a physical effect that's been studied for many years, not always very well understood. It's called either the universal dielectric response or John Scher's law. This growth in the absorption coefficient, the refractive index, though, is pretty flat. And we can do experiments for various plastics. Again, the losses grow rapidly. So materials that are low loss for millimeter wave applications may not be so good if we're pushing applications up to, I don't know, hundreds of gigahertz. So maybe we're interested in very high frequency RF front ends. We might be interested in antenna substrates or transmission line substrates and the like. So we need to worry about these losses. And there's a report that was published for INEMI that I wrote reviewing the state of the art related to high frequency evaluation of materials. And the URL is at the bottom of the page, so it's freely available. Okay, let me go to yet another example for packaging. This is not very fancy, so this is a bit old-fashioned. Conformal coatings. So conformal coatings are important to protect mounted electronics on PCB and other mounted electronics. There is no really good way to map out conformal coating thickness on a fine scale. There are examples where test samples can be made and then studied by deltascope. One can do destructive testing, but there are not many good options for non-destructive evaluation. So this work was done with a work group at INEMI. Some test samples were made. So this is fairly large. This is many millimeters. So it has this serpentine metallization on SiO2. The whole thing is then mounted on PCB, and then it's coated with the conformal coating. In this case, acrylic, though we've studied other conformal coatings. So the question is, how thick is that coating as a function of position? If the conformal coating is too thin, it may not protect the underlying material. If the conformal coating is too thick, it might stress the underlying material or be too difficult to remove should repairs be required. So here's some examples, and here we are going to show B scans. The first on the left, A, is along this metal at a position on top of the serpentine metal. The B is between the metallization, and C is across. So what we see here is the bottom. So the terahertz signal comes up from the bottom and is reflected down. So here we see the air conformal coating interface. Here we see the conformal coating metal or SiO2 interface. And we don't see anything up here because the metallization blocks the propagation of the terahertz field any further into the material. Now here, between the metallization, we see the back interface of the SiO2 substrate, or if we go across, we can actually see that shadow effect at different positions. So in all cases, by looking at what happens at the bottom, we can extract the conformal coating thickness. And here are those three examples. On the left is along this cross section, and we see that the conformal coating thickness varies in two ways. It varies between the metal and between the metal, and also there's an overall trend of inhomogeneity. So this rapid variation we think is due to differential wetting of the acrylic that's sprayed onto the structure on metal and on the SiO2. And these measurements here are made for these sections here. So this is on the metal, which is thicker, and this is between the metal, not on the metal, which is thinner. So we're talking about thicknesses in the range of 50-something microns to 60-something microns thick. So that's relatively thick. So that isn't a very hard measurement to do or to analyze, but it's a potentially important application where there are really no good alternatives. So let's now get to really advanced packaging. So here we're going to look at a complicated stack up, a multi-layer interposer. And this is a test sample. And the idea is, so here is this interposer, and this is for 2.5D integration. And you see there are chiplets, and various functionality devices mounted on this. There are multiple layers in the stack up. There are vias, metallization of multiple layers. This is a structure, just looking at the interposer, not the mounted structures. The interposer itself presents a formidable problem for non-destructive evaluation. How do we figure out if there are defects incorporated here? Certainly, there's a very important role for electrical testing, but what about structural tests? So here is the test sample, a schematic cross-section. There's a glass core in this interposer, and then there are multiple layers of ABF film of different thicknesses, 15 microns and other thicknesses. And there's metallization at multiple levels. There are vias through the ABF film. Okay, so there are basically two types of metallized structures in this test sample. There's daisy chains. So these are metal patches that go up and down between two different levels. They're electrically connected. And there's line space structures. These are just closely spaced metal lines. Okay, so the presence of metal is going to present a problem for terahertz because terahertz is not going to be able to see through patches of metal. But surprisingly, we can see through these lines by using the terahertz polarization. So this is just a top view of the test sample showing these different test patterns of line space and daisy chain. Okay, so polarization. So depending upon the terahertz polarization, linear polarization, we can see through these lines and we can see lower lying defects. So if the polarization is horizontal, we can see through the lines. If it's vertical here, the signal is reflected. And we understand that it's basically a plasmon-polariton effect, that there's a different screening of the incident terahertz field depending upon the polarization that accounts for this effect. So it means that we actually can see through some metallization. Not all, we can't see through the daisy chain, but through these lines. And we can detect certain kinds of defects in this structure. So we can measure warpage. So when these stack-ups are produced, there can be quite a bit of internal stress because the various ABF films are cured, there's metallization, there's thermal cycling. So that can produce overall warpage or local warpage in different layers. So we can look for warpage. So here's warpage seen in one of the ABF or several of the ABF layers. Okay, so this is subsurface information. These are cross-sectional images. We can also see delamination. So we'll see this also in the subsequent slide. Areas where there are bubbles or regions where the layers did not fuse or incorporate air bubbles inside. So we can also see that from the top using clustering methods. So here's an example of unsupervised machine learning, seeing some incorporated air, rather large regions, which, I mean, we see inhomogeneities in the just a plain C scan based upon the maximum signal, but this cloudiness is not necessarily connected to delamination. We see this kind of cloudiness where there is no delamination as well. So we really need this sort of analysis to extract these regions where there may be delamination. Okay, so there are other sorts of defects we've seen, but in the interest of time, I want to move on. And here's another example of advanced packaging. Here we're going to look at ABF put on top of an embedded die in a glass substrate with a recess. So here's the structure, the top view. So it's a glass substrate, 200 microns thick. There's a recess cut out of it, this square recess, and a die that's the same size is put in. This is a rather large die. It's just a test structure. The die has vias, rather large vias in it. And so basically, here's the glass substrate. The die is dropped into that recess. The recess has to be a little bit bigger than the die to get it in there. And then ABF film is put on the top and the bottom of that assembly. So what we want to do is we want to map out the thickness of that ABF film, because what's that might tell us is how does the ABF while it's cured flow? And we're going to see that the ABF film after curing is not uniform across this structure. Okay, so here again, this is a Terahertz C-scan, but here we're basically mapping the information we extract for the thickness of the ABF. This is on the front side. The ABF thickness actually ranges here from about 10 microns up to about 30 something microns. So some of this is an artifact. However, some of this is real. For example, over the vias in the die, excuse me, the ABF film is thinned as well as around the edges of the die. So what happens, we think, is that as the ABF is cured, that there's some flow of the ABF, into those gaps, whether they're vias or around the die, that produce a thinning of the ABF. This also occurs on the backside of the same structure. So this is an interesting sample. We're also interested in seeing can we detect cracks in the glasses, because in these structures, there's a lot of stress induced, around, especially around these corners, when these recesses are produced in the glass substrate. So we're currently, we hope, getting samples that have engineered cracks in them, and we hope, be studying those samples shortly. So with that, I'm reaching about 45 minutes. So I think it's a good time to wrap up. So my conclusions are rather brief. I want to point out, first of all, that Terahertz spectroscopy is going to be interesting eventually, not immediately, but one day perhaps, for 5G and 6G applications, maybe for RF front ends, antenna and transmission line substrates, and things of that sort. So we're going to need to know what materials are sufficiently low loss for these applications in the future. So that's spectroscopy. We spent a lot of time on Terahertz time-of-flight tomography for non-destructive evaluation, so to find defects, to characterize the thickness of layers. Again, the signal processing and machine learning is the key to getting useful information here. It can give axial super resolution down to and even less than, in some cases, 5 microns, despite the fact that the actual resolution, optical resolution physically, is longer given the wavelengths involved in our useful band. Costs are coming down, so people who might be reluctant to consider this at around $200,000 might rethink things when the costs are closer to $50,000. So I would be happy to field questions. So my email address is here, should anybody wish to contact me. The work that I showed was done in collaboration and with a number of students and postdocs and other collaborators outside of our group to whom we're grateful. Funding was kind of indicated in some places. ArcelorMittal, INEMI. We have also some projects funded by the government of France. We're also have some projects internally funded through the Georgia Tech 3D Packaging Research Center. So with that, I'll conclude, and thank you very much for your attention. And again, I encourage you to contact me if you have any questions or comments.
Thank you, Dr. Citrin. Now we are open to the Q&A session. So if you raise your hands, I will allow you to speak in this session. If you, from the attendees. All right, Dr. O, do you have a question?
Yeah, thank you for the great presentation. And I'm not familiar with this field, but so I want to give several basic questions about this research. The first one is, I think if in the B scan, the signals go reflections several times, and the last signal might be very minimal. So is there any limitations to get the discernible signals, the layers of each the total devices?
Yes, good question. So how thick a sample can we study? It depends upon two things, the materials, how lossy they are. So in the case of that stack up, we can see fairly thick deep into it. We can see into the glass and through the glass, but it's a little bit complicated because the metal prevents us, depending upon where we are, of seeing deep, beyond the metallization into the sample. So just looking at the materials to give you a rough idea, because it really depends upon what the material is, typically between a millimeter and centimeters of material is the depth we can see into. Now, I mentioned losses, the loss tangent, so that's obviously important. Another important factor is dispersion, so the frequency-dependent refractive index. So in some materials, that distorts the signal as it propagates through more material. We do know how to treat that problem from the signal processing point of view. But again, it depends upon the material and what we're studying. I should also mention, yes, you point out that from features that are deeper in the material, you get a weaker reflected signal. Absolutely true, due to the losses and also due to shadow effects. So if you already get a good reflection from something above, there's less signal propagating to deeper structures. So the deeper you go, not only is there, just loss in the materials, but if there are features that produce reflections, you're losing more and more signal deeper into the structure due to those reflections. To some extent, we can account for that, but eventually we're going to lose the signal. And again, it depends upon sort of structure.
Thank you. I have one more question.
Yes.
And through the scanning measurements, there might be a little structure difference or material difference. I think it makes some noise in the signal. So is there any filtering techniques to get the proper signals to detect the defects in the devices or some other problems in the total structure of the device?
Yeah, so different sorts of noise. First of all, there's noise intrinsic in the measurement. So this is non-additive noise, so we can't signal average it out. And there's not much we can do about it. So that's why the signal falls off at around 3 terahertz. There's nothing more we can do at higher frequencies. But there's also, I don't know if I want to call it noise, but due to inhomogeneities in the material, the signal might vary depending upon position. In most of the materials that I discussed today, the material itself is fairly homogeneous. These polymers don't have very big spatially dependent refractive indices. You have to work hard to see any of those effects. So that's not a problem. Now, to deal with noise, yes, there's certainly filtering we do. So there's noise at high frequency, at low frequency. So we have to filter. But I mean, the way we deal with noise, apart from filtering, which is very useful, is our signal processing techniques are designed in some sense to defeat the presence of noise. So if you look at some of our papers, which are easy to find on Google Scholar, just by looking up my name, you'll see how we do this deconvolution. I did not want to spend time on it because it's rather technical, but it's very important. So we use techniques, for example, called sparsity-based deconvolution or autoregressive spectral extrapolation. So if you look at our papers, you can see detailed discussion of that. And those techniques are specifically designed to deal with the problem of noise. Now, they're not perfect. In the end, if there's noise, that's going to limit what we can do, and there's always noise. But that's precisely where we have to work hard to deal with the noise. But it's not just filtering, although filtering is important. It's much more than simply filtering.
Thank you.
All right. Any final questions from the attendees? If not, can I ask a question?
Absolutely.
Yeah, it might be a stupid question, but you explained about the examples about the non-destructive NDEs for the dielectric layers on the metallic substrate, right?
Mhm.
How about the reverse applications in detecting like a tracing metal contamination of the like micro-sized particles inside of the dielectric media
Yeah.
or something like that?
So this is something interesting, which we actually had thought about in the past and had talked to some people, but never found a partner. So, for example, companies that smelt rare earth metals are interested in recovering small particles from the slag. So we were interested in trying to detect metal particles in the slag, which is a ceramic or glassy-like material. We never did it, but it's certainly an interesting sort of problem. Yep, you're absolutely right. It is a potential application.
Thank you. So, let's thank our speaker, Dr. Citrin. And then thank you for your time and for your amazing talk. And I'm looking forward to working with you in some future. So thank you for your time and have a good night.
Thank you.
Thank you. Now we conclude this webinar session. Thank you for your participation. And if you have any questions, you can send an email to Dr. Citrin or me. And have a good night. Thank you.